Okay, so this is your video for 3.4, and it's a really short section, but it's really important. A lot of this stuff ties in all of our perpendicular and our corresponding and alternate interior, parallel and alternate interior and all that we did in the first couple of sections. It kind of ties all those together and adds another dimension. And then some of these proofs we use later on in the 6 weeks and on into the rest of the semester. So it stays pretty important. So hold on to it. This is the one that people miss the most if they're going to miss something on this first test, is the perpendicular stuff. So you might want to watch it twice. I need you to take very good notes, including your margins and your summaries, or I will take off for those. Okay, so I already kind of started filling in some stuff for you. The shortest distance, the shortest segment from a point to the line is the perpendicular segment to that line. The perpendicular segment to that line. So if you're going to be the shortest, you want to go straight there, and perpendicular is going to get you straight there. Remember, when we're looking for perpendicular, we know we found perpendicular when we see a right angle. It means perpendicular. Okay, so in this first picture here, the shortest segment from point P to line AC would be the perpendicular segment, and the perpendicular segment would be PB. We know we found PB, we know it's the shortest because the right angle tells me perpendicular. So we're going to write and solve an inequality for x. So if PB is the shorter segment, then I could say x plus 3 has to be greater than 5. Now think, do I want an equal sign? Can these be equal segments? No, because PB is the shortest, so even if x plus 3 is just a tiny bit longer, it still has to be longer. It can't be the shortest. So x plus 3 is greater than 5. Remember, solving inequalities is exactly like solving equations unless you're multiplying or dividing by a negative, which I am not here. So I solve exactly as normal. X is greater than 2. So as long as x is bigger than 2, then PB can still be the shortest segment. It can be 2.001, it can be 2.3, it can be 58. As long as it's bigger than 2, then I'm good. Okay, pause here and try the second one with the diagram right below this. Okay, so in this case, x minus 5 is your perpendicular segment. He's the shortest. So this time, x minus 5 has to be less than 12. 12 has to be the bigger guy. Still going to move my 5 over. So as long as x is less than 17, then we're good. Now, you might also think about this logically. This segment has to be bigger than 0 for this to work. So you could put another segment on here saying that x has to be bigger than 5, but less than 17. That way it doesn't turn out negative. Because think about it. If x was 4, 4 minus 5 would be negative 1. Can AB be negative 1? No, of course not. So this is just helping us stay in the positive, and this is making sure that it stays the shortest segment, that it stays perpendicular. Okay, let's move on to what we're really talking about today. So go in your vocabulary grid and read those first 3 theorems, 341, 342, which is the perpendicular transversal theorem, and 343. Now, these are numbered 3, 4, 1, 2, and 3 because this is Chapter 3, Section 4. It's the first theorem. And then perpendicular transversal theorem. And then 343 is Chapter 3, Section 4, the third theorem. We don't get to call them 341 and 343 because if you were using a different textbook, it wouldn't be Chapter 3, Section 4. But that's just helping us find them. So you'll notice in the parenthesis, I don't know if you can see this on yours, if you'll notice in the parenthesis, oh my gosh, I stink, what you're calling these. So 343, when you're going to write it in a proof, you're going to write 2 lines perpendicular to the same line, means the 2 lines are parallel. You can't use the shortcut numbers because if a person didn't have your textbook, they wouldn't know what you were talking about. Okay, so first up we are going to write a proof for the perpendicular transversal theorem. That means we can't use it in our proof. We're just going to explain to people why it's true. So here's our given, that these 2 lines are parallel and this line is perpendicular to BC. We want to prove that AB is also perpendicular to DE. So here's our choices over here. So the first thing we're going to fill in is our given. we're going to go ahead and put all of our givens, or both of our givens in the same spot so I don't have to come back and get them later. Okay, and we can also put our proof down here in the bottom. AB is perpendicular to DE. Okay, so the setup we have, this is important because this is how you're going to know when to use perpendicular transversal theorem later. So when you see this setup, two lines are parallel and there's a line crossing through there and you know it's perpendicular to one line, we're going to prove why it must be perpendicular to the other. Okay, so here we start. Measure of angle ABC is 90 degrees. How do we know this is 90? Well, we know it because it told us that those lines were perpendicular. So, perpendicular vocabulary word here, definition of that on the other side. Now it's telling me I'm going to use the corresponding angles postulate, which we know from section 2. And that says if two lines are parallel, then any corresponding angle is congruent. So I want this one to be my corresponding and his partner BDE down here. So we say angle ABC is congruent to BDE. Now that is a matter of knowing your postulate, saying that if the lines are parallel, then corresponding angles are congruent. So I'm going to star in congruent. Now, after we go to congruent, this one's an equal, this one's incongruent, so I need them to match up. So I'm going to go ahead and swap this over into equality. Excuse me. And you know we do that by definition of congruent angles. Now it's saying that BDE is equal to 90 as well. Well, if ABC was 90, and ABC and BDE are the same thing, then that makes sense that I could swap this out and BDE would also be 90 degrees. Now on this one, if you were doing this by yourself, you could choose substitution or transitive. But since we have our answers on the side, we'll go with what they gave us. But you could have used either one, transitive or substitution. Now, if AB and DE are forming a right angle, then that must mean that those lines are perpendicular. So I'm going to use definition of perpendicular backwards this time. If the angle's 90, that must mean the lines are parallel. We saw this with supplementary in the last chapter. If angles are supplementary, they add up to 180. If angles add up to 180, they're supplementary. Good definitions go forward and backward. Okay, perpendicular transversal theorem is super important. It's the most important one out of this chapter. So take a second to reread this proof and make sure it makes sense. Bottom line, when you see this setup, two lines are parallel, one of them's perpendicular, that must mean the other one is perpendicular. That is the big idea out of this proof and out of this section, actually. Okay, so we have a short proof for this one. Here we go. So I know that if AD is parallel to BC, that's already marked. AD is perpendicular to AB, that's marked with this right angle. And BC is perpendicular to DC. I want to prove that that must mean these top and bottom lines have to be parallel as well. Okay. So it's only a three-step proof, so we must be shoving all of our givens into this first statement. AD is parallel to BC, AD is perpendicular to AB, and BC is perpendicular to DC. Okay, so we put all our givens in the first one, and we're going to put our proof in the last one. So, only one more step for me to fill out here. Given all of this stuff, why does that mean that AD is perpendicular to DC? Well, if you look back at your previous theorems, that is the perpendicular transversal theorem that we just saw. So look back at the setup that we just had a second ago and compare it to the setup that we have just now, if I can get out of my own way. We know these two lines are parallel, just like I knew these lines were parallel. I knew that this angle was a right angle, just like I knew this was perpendicular. So perpendicular here. What did I figure out? Well, that must mean this other one is perpendicular. So that must mean this other one is perpendicular. Do you see the similar setup from what we used before to what we're using now? That's why I get to skip all the steps I did on the last proof and go directly to perpendicular transversal theorem. Okay, so this is everything we just did in this last proof, all 6 steps, wrapped into one step right there. Perpendicular transversal theorem. Go back and reread it if this is not making sense. Okay, now if these are perpendicular, AD and DC are perpendicular, then why does that mean these top 2 lines are parallel? And this is actually theorem 343, but remember we can't call it that in case somebody else is using a different textbook. So we kind of summarize what the theorem says. If 2 lines are perpendicular to the same line, then that must mean those 2 lines are parallel. And that's what we have here. We have AD being perpendicular to the bottom and the top. And if you're perpendicular to the same thing, the other ones must be going the same direction at the same speed. If you're going to get a 90 and a 90, these two have got to be going the same way. So that's what that 343 says in action. And there is no substitute for knowing these 2 theorems forward and backward. If I don't know what these 2 theorems say, I have no clue how to do this proof. Okay, so you've got to know your theorems from this chapter very, very well to be successful here. Okay, last example here, not a proof. Hooray! Rip currents may be caused by a sandbar being parallel to the shoreline. And we have 2 pictures of this going on here. Waves cause a buildup of water between the sandbar and the shoreline. And when this water breaks through the sandbar, it flows out in a direction that is perpendicular to the sandbar. So you have kind of what's going on here. Shoreline and sandbar are parallel, so we can see it marked here. And then when the water builds up, it's going to build up all this pressure in here, and it's finally going to shoot through the sandbar, and it's going to shoot through in a way that it's going to be perpendicular. Okay, rip currents are very dangerous because people can get stuck in here, and that's where people drown. So understanding them is important for lifeguards and things like that. Why must the rip current be perpendicular to the shoreline? So they told us that the rip current was perpendicular to the sandbar. They told us that the sandbar and the shoreline are parallel. So why does that mean that this is perpendicular? And that is another example of the perpendicular transversal theorem. And it says if 2 lines are parallel and a transversal is perpendicular to one line, it must be perpendicular to the other. Okay? If these 2 are parallel and going exactly even, there's no way that this could be perpendicular to one and not the other. So that's what the transversal theorem says. Okay, part B. A swimmer who gets caught in a rip current should swim in a direction that is perpendicular to the current. So they don't want you swimming with the current, otherwise you're going to get swept out to sea out here and it's going to be harder to rescue you. So they're saying if you're stuck in here, you should swim in a direction that is perpendicular to the current. So why would that be swimming parallel to the shoreline? And that is the converse of the perpendicular transversal theorem. Because that would say if I want to swim perpendicular to the transversal, that means I'm going to be headed this way. If I want to be perpendicular to the transversal, there's no other choice but for me to be parallel to the shoreline. So the converse of the perpendicular transversal theorem says being perpendicular to the transversal means you're parallel to the shore. Okay, and that's really counterintuitive to what people think when they're stuck out here drowning. They think, I need to get to the shore, I need to get there as fast as possible. So if I'm stuck out here, here's me stuck out here drowning, their thought is to swim to the shore. But when you do that, you're actually fighting all the force of the water, and so you're just getting caught and tired, more and more tired as you get caught in the water. So what you do is you swim parallel to the shore until you get out of the current, and then you can turn and swim towards the shore. But a lot of people drown because they spend all their energy trying to swim straight to shore. So don't be one of those people next time you're out there caught in a rip current. Okay, so short notes today. So read especially back over those 2 proofs that we did, and read over those 3 theorems in this section because they are so, so, so important. Okay, see you tomorrow.